right? So at least to, right, let me just okay. So this is an advanced technique, okay, and hardly being explored in Malaysia. So that's why if we have like at least some knowledge on electrochemistry, you can use electrochemistry not just in biosensor or chemical sensor, but also the electrochemistry can be used in other study, for example, corrosion. That's what comes in my mind, but there are other applications of electrochemical techniques. So at least some ideas of how the electrochemical, the basis of electrochemical techniques, at least you have some ideas. I think you during our school, secondary schools, I think you have come across galvanic cell, okay, or electrolytic cell. I don't know what are the names that being used, okay, but these are the common terms that being used, okay, during study undergraduates or probably in school, yes, secondary school. So you can see that when we talk about galvanic cell, we are talking about, where is it? Okay, we are talking about all this. This is, sorry, this is under electrolytic cell, okay? So galvanic cell is potentiometry. Sorry, it has to go down there, right? Okay, so galvanic cell is potentiometry, known as potentiometry, whereas electrolytic cell is where we have voltammetry, amperometric. Usually we don't discuss this one. All right, so I'm not going to discuss the to the extreme theoretical of electrochemistry, but enough for us to understand what needs to be studied if you are to develop biosensor or chemical sensor. What are the things that you need to understand in order to use electrochemical techniques, yeah, right? Okay, so these are the basics, right? But of course, nowadays we don't really use this very bulky setup, okay? Nowadays we are using a very simple printed electrode, yeah? This is printed. Okay, so it is much easier. You can see, let me compare this printed electrode with the what we call as conventional setup, okay? So for the voltammetry cell, okay, so I'm not referring to potentiometry, I'm referring to this technique, okay. Commonly, we have 3 sets of electrodes, which is compulsory, okay, 3 sets of electrode. We have the most important one, working, where you put all your whatever material, nanomaterial on top of the working electrodes. You also need counter electrode, because counter, this is where, okay, you can see if the electron between the working and the counter is completing the circuit, okay? So remember that in your bachelor years, you learn about anode, cathode, okay? So this is what we have previously called anode and cathode. So for the circuit to be completed, it requires a counter electrode to complete the circuit, yeah? We also have reference electrode, okay? this is to stabilize the potential. Yeah, this is to stabilize the potential. If we don't have reference electrode, then the reading, the background reading will be not smooth. Yeah, so that's why we need to have reference electrode. Okay. And particularly, so this is the working electrode on enlarged, yeah? Working electrode. So you can see that the surface here, okay, this is what happened. Okay, you have your analytes, okay, and you have a redox process. Okay. Okay, redox is actually reduction and oxidation. So it's a combination of reduction and oxidation. So it is called a redox process. Okay, so your analytes has to move towards the surface of electrode, and then you will have an electron transfer between your analytes with the surface of working electrode. So this is more or less what is happening, but of course it's more than that. This is the most basic that happen on the electrode, near to the electrode. Okay, so we look at here, this is the printed electrode. So same structure, we have reference electrode, and usually we have Ag, AgCl. So Ag is silver chloride. So there are other types of reference electrode. And then we have counter electrodes. So you can see that here counter electrode it looks like it's a platinum wire. Okay, here is platinum, but then you can also use carbon. Yeah. So here the printed electrode, the counter electrode is carbon, and the working electrode also here, the example is carbon. But the working electrode can be other things, like we also use gold, okay, and different types of material. It's up to you. I mean, there are a series of options that you can use. It depends also on what is the application. So usually we use gold and carbon. So carbon has a very high conducting current in terms of current, but it has some disadvantages. So this is just a connection. So instead of here, you will have this connection connected to what we call as potential stat. Yeah. So these are the basic structure of electrode. Okay. So this is the whole what we call as potential stat. Yeah? Potential stat. Yeah? Let me write it down. Okay, do not confuse the name of potential stat with potentiometry. Okay, potentiometry is the technique. Okay, potential stat is the machine. Okay, so the one we are discussing is voltammetry. So using machines called potential stat. So this is the basic structure of potential stat. And of course, we are not discussing the circuit or whatever, because we are not going to do prototype. Yeah, this requires engineer, those who are well versed in electronic parts to do the prototype for us. So what we don't actually. I'm as a chemist, we don't do this job. We just need to know the structure so that we understand how it works. So again, these are the usage of all different parts, all different types of electrode. Of course, working electrode is where the redox process happens. Means that the analytes will undergoes reduction and oxidation. The reference electrode, as I mentioned, is to control the potential so that you have a nice background reading. And counter electrode, sometimes you have platinum, Just now I showed you, it can be also carbon. Okay, conducts electron from signal source means that from the working electrode, to complete the circuit. Actually, it's easier if we understand to complete the circuit. Yeah. Now the last one that I didn't show is supporting electrolytes. Okay, so since this one, you can see that we have to put some electrolytes here. Okay, and this also has to be deep. Okay, inside electrolyte, supporting electrolyte. Okay, so this supporting electrolyte is the one that you be used to. It can be also used to dissolve the analyte of interest. The one that we want to measure, we can dissolve it in supporting electrolyte. So there are many types of supporting electrolytes. Okay, why we need to have supporting electrolyte is to enhance the movement of electron. Excess of negative. Because without supporting electrolyte, then it's a bit difficult for the redox process, okay, to happen. So this reaction has to happen in the supporting electrolyte. So there are many types of supporting electrolyte. We can use KCl, potassium chloride. Okay, we can use phosphate buffer solution. And there are many types. And there are many types of supporting electrolyte. Depends on the, sometimes we have to do some study because the analytes probably suitable in potassium chloride or suitable in phosphate buffer solution. So we have to look at the suitability. So now we look at the detail, what happened on the surface of the working electrode. So as I mentioned, it's not as easy. If your analyte, if your glucose, for example, glucose is not conducting. So let me choose another one. Where is the button? Okay, let me choose plumbum ion. Okay, so you have dissolved the plumbum ion. Okay, now if you are to you want to analyze, you want to identify the concentration, or you want to confirm the plumbum 2 plus is in the sample, for example. So you dissolve the salt, or you have the samples, you do some pre-treatment, okay? So you have to imagine that you have a lot of Pb2 plus in the sample. So before it can be reduced, okay, the plumbum has to move here. So the distance, okay, between the analytes and the electrode is very important. Okay, so if you want to know more, this is what we call as quantum tunneling effect. So the distance should not be, it should be around, I forgot, this is around 50 nanometers, but I have to check back. Okay, so if it is too far, means that your beaker is very big and your electrode surface is far away from your analyte, then you're not going to have a very good redox process. So another one that you can do is to use stirring. Why? Because we want the analyte to move towards the surface of electrode. So this is what we call as mass transfer, okay? Because the movement requires the analyte, the system requires the analyte to move. So please don't imagine that they walk like us. No, they have to. It's not simply that they can move. So that's why sometimes you have to stir. Okay, so that the analyte move towards the electrode, the surface of electrode. So after some distance, then you can see the chemical reactions can start to happen. So there is a certain gap that you have to make sure the analyte is close to the electrode. Okay, so there are a few things when we do a chemical reaction in the electrochemical system. Okay, one of we have to think about the mass transfer. So if you have a very viscous sample, then it's not going to work. Okay, you have to dissolve it, you have to dilute in certain solvent. Okay, and usually organic solvent does not work. It's a bit difficult. It can be, we have done that, but then it's a bit difficult. Electron is electron, yeah, not election. Electron transfer occur at the electrode surface. So if you can like enhance, yeah, this process, okay, if you can enhance the electron transfer, there are many ways to enhance the electron transfer. You can have a very good reading, okay, a very sensitive technique, okay, provided that you can enhance the electron transfer. There are many ways. One is using a good supporting electrolytes. The other one is putting some nano materials. Yeah? There are many ways to enhance the electron transfer. Chemical reactions proceeding, okay, they might be homogeneous, they might be heterogeneous, depends on your analyte as well as of the electrode of interest. Yeah? The surface reaction such as adsorption, desorption, okay, that one also might happen. Okay, usually when we do development of biosensors or chemical sensors, we do what we call as surface modification here. Okay, so as I mentioned before, if you want to enhance the electron transfer, we put nanoparticles, metal nanoparticles, yeah? Because there are some, of course, theories saying that nanoparticles, metal nanoparticles, can electrocatalyze. Means that it helps the electron move faster, okay, move faster to the surface of electrode, right? So this one we do. And also, if you remember, this is where we put all the biomarkers. The DNA, the antibody. So this is where we put the biomarkers. Okay, and sometimes organic materials like DNA, antibody, they can inhibit, they can reduce the conductivity. So we have to balance how much, and then that's why we have to combine with nanoparticles, metal nanoparticles, conducting polymer to help increase the to enhance the electron transfer, so that whenever we put the biomarkers, it will not lower down the current produced, because in electrochemistry we rely on current. We rely on current, so it's no longer just in spectroscopy we rely on wavelength, intensity, but in electrochemistry we rely on current reading. Okay. So in short, these are the factors, okay, that we need to control. So whenever that we develop, okay, we have to think about the surface area of the working electrodes, especially what material that we want to use, geometry, mean the shape, okay, and the surface condition, okay. And during the process, we have to control temperature. Usually pressure is not a concern because we dip it in solution. So it's normal pressure inside aqueous solution. And the time of reaction, because you can see that it requires time for the analyte to go to the electrode surface. So we have to think about the time. We need to consider what is the response time, whether you're going to have a very fast reading or it's going to be slow. Right. The other issue is, okay, because of this, okay, we need to consider material because it regards to how the sample will diffuse. Okay, this one, of course, when we study or when we develop electrochemical technique for detection, we have to consider the effect of electrolyte, pH, okay, concentration as well. Okay, so this usually among that we study. Okay, and we can identify, okay, because there are quite a number of electroanalytical techniques. Just now I showed to you, so you have to decide which one. Okay, so this one we will focus only on voltammetry. We don't discuss potentiometry. Okay, even though potentiometry is quite famous. So if you are used to pH meter, okay, when you use the pH meter, it's actually based on potentiometry. Okay, right. Okay, so this one is telling us what is the difference between potentiometry and voltammetry. Okay, so potentiometry, not potentiostat, yeah, potentiometry is to measure potential of sample or system with the electrode. So this is very common, the one that we, I don't know, many of you probably who has taken electrochemical methods during your bachelor, you will know about electrode potential. Okay, so as I mentioned just now, pH meter, when you dip the electrode, okay, in the solution and get your pH reading, so that is potentiometry. Okay, it's actually measuring the potential difference between the solution that you dip with the electrode, yeah, electrode of the pH meter. So that's how you get the reading of pH. So, but for biosensor and chemical sensor, we usually use voltammetry. Okay, so for voltammetry, what's the difference is, I think I have it here now. We will discuss detail on voltammetry after we finish this. Yeah, so we are going to focus on voltammetry because it is more robust compared to potentiometry. Okay. Okay, electrochemical biosensors, okay. This is what we have learned, okay. Remember the hybridization, okay. The hybridization of DNA, we have probe DNA, and then we have target DNA. You have a good hybridization forming what we call as double-stranded DNA, yeah. So I mentioned before during the discussion, the principle of DNA biosensor to tell us whether it's yes, mean it is positive, you have E. coli in the system, for example, or no, you don't have E. coli in your drinking water. It is based on hybridization. But of course, you cannot look at the system and tell straight away, oh, okay, this is 100% hybridization, this is 50% hybridization. We need an indicator, okay? So in order to tell whether you have a very perfect, a perfect hybridization or probably weak hybridization, we need an indicator. So you can see that here, the indicator, okay, it is called, usually, sometimes we call it label, yeah, indicator, label, tag, okay. So these are the examples of indicator that gives us the information whether you have a good hybridization or you have a weak hybridization, because you cannot tell by looking at the beaker. You have to look at what the current reading, or if you use optical, you have to look at the color change. Okay. So in this topic, we are talking about electrochemistry. So we are talking about electrochemically active label. Yeah. So sometimes for DNA biosensor, we call it hybridization indicator. So the word indicator should at least give you some idea. It tells us about the hybridization, whether it is complete, strong, or is weak. So there are few mechanisms. Yeah? There are few mechanisms of how hybridization indicator or the label can interact with the double-stranded DNA. So we have electrostatic interaction. We have groove binder. Okay, groove binder can interact via major as well as minor groove binder. We have intercalation process. Okay, so this is mainly that we use major groove binder and intercalation process. So do not trouble yourself if it is complicated. It's just a simple process. One is intercalating, means that it goes inside the double-stranded DNA because of the interaction. Remember that there are phosphate backbone here, okay? And then major groove binder is just hydrogen bond, okay? So it's not that difficult, but we look through what are the examples of intercalators. Okay, there are so many names. Yeah? Now I mentioned intercalators and major groove binders. Yeah? So the function is to tell us whether you have a very good hybridization happen or you actually have a weak hybridization, because you cannot tell just by looking. It does not show you anything, right? So the electrochemical label, whether it is intercalators, okay, this is the mechanism of how it binds with the DNA, or major groove binders, okay. These are types of electrochemical label that we have. So usually intercalators and groove binders, they are organic compound, okay. But sometimes it is also for intercalators, it can be metal complexes, okay. And there are other types of label, neither intercalators or groove binders. Yeah? It does not interact via that way, but we can also use metal nanoparticles. But let us focus on these two first. So this is an example. This is an example called very common DNA intercalator, or the name hybridization indicator. It is called methylene blue. Yeah. Okay. So how does it work? So remember back, this is the probe DNA, and then you have the target. Okay. And if they form a very strong hybridization, okay, this methylene blue will intercalate. This methylene blue will intercalate inside the double helix structure of the double strand DNA. Okay, so it seems that methylene blue has high affinity to intercalate with double strand DNA. So what happened is, if we have a good hybridization, mean perfect hybridization, there'll be a lot of methylene blue intercalated inside the double strand. So since methylene blue is electrochemically active. Yeah, you can see that it is can be reduced and oxidized. So it is electrochemically active. Chemically active. So if you have that inside the hybridized DNA, it can tell you how much, okay, how good the hybridization rate. So if there is a lot, means that your hybridization is very good, then that it is an indicator of yes, positive, you have that virus, positive, you have that bacteria or whatsoever. So if it is not good, means that the hybridization is very low, indicated by a low amount of methylene blue intercalated in the double strand DNA, then it shows that it might be negative sample. Might be. So that's how it works in electrochemical DNA biosensor. We have to expose the hybridized DNA with what we call as DNA intercalator. So this is the process I have showed you before. Okay, this is again the DNA probe, and then attached to the electrode. Okay, you can see this is the electrode, working electrode, and then we expose DNA from the sample, extracted from the sample, and hybridization occur, right? So after that, we expose the whole set with methylene blue, the hybridization indicator, and the methylene blue will intercalate. Yeah, you can see that there are blue colors. Okay, will be intercalated inside the double helix structure of the DNA. So you can see the current change, from before and after. So you can see it might goes down, then it might goes up. So this one I'm not going to tell you why, because it requires, unless you want to do research. Unless you want to do research, there are sometimes that it goes down, and there are sometimes it goes up. Yeah, but in general, the more methylene blue, which is electroactive, then you should have a high current. Okay, this one, it goes down, there are certain issues. Depends on which voltage that you are interested of. Yeah, so this is basically how we read, yeah, the indication whether you have a good hybridization or you have a very weak hybridization using a redox indicator, right? This is another type of indicator, okay? So it's also organic compound. So you can see a lot of synthetic chemists, organic chemists, they are the one who usually do the organic synthesis. And if you look at the structure, or we don't have the structure, okay, the structure of methylene blue, you can see that commonly we have rings structure. Ring structure in S indicator, hybridization indicator. So if you look at here also, there's a lot of rings. And this one, okay, the structure of the hybridization indicator actually indicates whether you have a very good DNA system, DNA biosensor system, or you might have a very not so good. Yeah. So as I mentioned, even though methylene blue is commonly used, right? But then it's not really selective, yeah, because you can see that if you understand the electrostatic attraction is between different charge, positive charge and negative charge. So even the single strand can also interact with methylene blue. So when we have that system, it's going to be interference. If you don't understand, it's okay. But the more complicated intercalator that we have, you can see that the structure is more complicated compared to the methylene blue, right? The more selective it is. We want the intercalator only to intercalate inside double strand. We do not want the intercalator to interact with the single strand, but it happens. So that's why we need to design the intercalator or the hybridization indicator to be selective, right? So it's not, for me as analytical chemist, we don't do that, but usually it's for the organic chemist or synthesis. Why? All right. So another one, if you remember in the list, we also have metal complex. Okay. So metal complex, also known as DNA intercalator. Okay. So these are example, ruthenium complex. They intercalate inside the DNA structure. And as we know, of course, metal, they are highly electroactive. Okay, you can see here the electron redox process happens here. Then, of course, you can have in terms of current, you will have an indication in terms of current change, whether you have a hybridization or you don't have a good hybridization. So this is how in general of how we use the metal complexes. This is ruthenium, so this is an example of ruthenium complex. So it's not that complicated. We just expose the DNA that is already hybridized into the solution of ruthenium complex. Okay, and this is another, these are all examples of groove binders. Okay, so groove binders, they are not intercalators. Okay, this is the structure of DNA. So this is where they bind with the DNA. Intercalators, they intercalate in the middle, right? So these are examples of organic compound that is function as groove binders. And usually the groove binders, they are crescent shape, crescent shape. You can see, so that's why they can bound at the groove side of the DNA. Okay. Right. So this is an example of how the mechanism of groove binders. So you can see sorry, this is not good. All right. Okay, let's forget about this. Okay, so these are another examples of groove binders. So this is how we confirm. This is how we confirm. So if we expose the DNA biosensor after hybridization, exposed to the groove binders, we can at least know if there is a good hybridization, then that means we can have a higher reading. And if we have a lower amount of hybridization, then we have a low reading. So this is how the groove binders work. And this is, of course, indicating negative sample, and probably it is indicating a positive sample. But a lot of work has to be done before we can confirm using this. So if you observe here, the groove binder A is much more easier to differentiate between positive or probably a good hybridization, compared to if you use like methylene blue. It's very difficult to identify the change, the difference. So that's why when I talk about the structure or the binders or the intercalators that we want to choose to indicate the hybridization. All right, and the last example that I mentioned just now is you can also use metal nanoparticle as the indicator, but it's quite difficult if we are using DNA. There's a lot of work to be done. So this is the DNA probe, okay? And then you have to attach, before the reaction, you have to attach the DNA with the metal nanoparticle. And this requires a very tedious process. And usually we don't do that, we give it to the experts. So that's why I don't really talk about it. So you can see here, another way of quantum dot is also considered metal nanoparticle. Okay, it's a bit complicated if you have to attach the metal nanoparticle to the DNA probe, and then whenever that they hybridize, you can see that these quantum dots or metal nanoparticle will give an indicator whether you have a very good hybridization or you have a very weak hybridization. But the process of combining metal nanoparticle with the DNA can be very tedious. It's quite difficult. So this is another example of using metal nanoparticle as the hybridization indicator. Okay, there are also what we call as labelers, meaning that electrochemical DNA biosensor, but we do not want to use any hybridization, what we call intercalators. We do not want to use any groove binders or metal complexes or metal nanoparticle. You just let them hybridize. Okay, there are techniques, okay, that can be used. One is what we call as EIS. Okay, so you can see from here, this is also under electrochemical technique. So this is the probe DNA, and then you expose to the extracted DNA, and if you have a good match, means that you are the sample is positive for whatever that you are looking for. So you can see there is a difference, okay, between the reading of just probe DNA and then when you have hybridization. No label is needed for EIS system. So this is a quite recent technique that many people now are exploring. You don't have to label using any indicators. You can just confirm through the reading of the EIS. Okay, yeah, 647. Electrochemical based immunosensor. So just now we talked a lot about DNA. So what about if we have antibody antigen interaction? Yeah, immuno. So everybody should now know at least what is immunobiosensor. So what type of electrochemical label that you can use? So these two are common: metal nanoparticle, enzyme. So this is the structure that I have introduced you before, the antibody set. And then when exposed to the antigen, antigen means the virus, the bacteria, the protein, for example, that indicate there is a virus, okay? So they start to interact with this antibody, okay? And then how are you going to confirm that there is an interaction? So we need to have what we call as label antibody. Okay, you can see here. First is capture antibody, which is here. And then the capture antibody will interact with the virus, with the bacteria. And then you have the label, right? This is what we call as label antibody. So, you know, the antibody has extra material, okay? In this case, the label is nanoparticle, metal nanoparticle, and specifically using magnetic, I think it's magnetic particle, magnetic particle. So the nanoparticle, okay, will give some signal, will give out signal indicating that there is an interaction between the capture antibody and the antigen, right? So let's say if there is no interaction, let me look at where is the, I cannot find, okay, I want to find the eraser, but cannot find the eraser. All right. Now, if let's say, okay, let's say there is no antigen, means that the virus is not there. Okay, the virus is not there. So the whatever that capture antibody will remain as capture antibody. Okay, so it's negative. So even the label antibody comes here. Okay, the label antibody, this one. Okay, it will not be able to interact with the capture antibody because the antigen is not there. Okay, so of course the correct one is here, but the negative one is here, right? Is this what happened? Yeah, so this is how it works. Means that if there is no label antibody, because you do washing and then everything is washed away, so what's left behind is only the capture antibody, and it should not be giving any signal. It should not, by right. Should not, but it's difficult to have that actually. Right? So this is also the same thing. I'm just giving a few examples. The red, this one is capture antibody, and the blue one is the antigen, the virus, the bacteria, the fungus, whatever that you are working on. And then you have the label antibody set that gives out the signal, yeah, indicating that there is an interaction between the capture antibody and the antigen. So imagine if it is a negative, means that the blue antigen is not there, so everything will be washed away. All this will be washed away, leaving only the capture antibody. So you will not be observing any signal. Okay. So another types of label, instead of metal nanoparticle, we can also use enzyme. This is quite common. Yeah. So you can see the same structure. This is the capture antibody. This is the antigen that you expose the system to. If it is there, then it's going to interact with the capture antibody. And to know whether the interaction is there, you have to use label antibody. So in this case, the label is using enzyme. And enzyme is an electroactive. Yeah? Enzyme is electroactive. So it will gives out current reading. So you get a response. Yeah. So same, if there is no antigen, then there will be no process of label antibody coming to the surface. You only have capture antibody. So again, this is another clear picture of how you can use enzyme label to indicate whether you have interaction between antibody and the right antigen target. So again, if you do not want to use label, there are labelless technique. We can use EIS again, impedance technique. Okay, so capture antibody exposed to the antigen. Okay, so you can directly observe there are changes straight away without using label. You don't have to use enzyme, you don't have to use metal nanoparticle. By using EIS, straight away you can use, we can detect the process. Yeah. So this one, I will not actually I do not want to discuss with you because it is in fact a bit complicated. Right? So it is enough for you to at least know the idea of how electrochemical techniques is being used. Right. So at least you can recall back the terms, oxidation and reduction. So receiving electron is reduction. Okay. and release electron is oxidation. Yeah? So this one, ferrum 3 plus being reduced to ferrum 2 plus. So this is the process that happens. As you can see, I mentioned just now that the distance from the electrode is very important. Okay, so if you can make it very near the analyte to be near to the electrode, then we can have a very good redox process happening, right? So if you look at here, okay, regardless if whatever, this is just an electrode, example of an electrode. So you can have stirred and unstirred solutions. So there are three processes happening, how the ions, the ferrum 3 just now move towards the electrode. So you can see we have the bulk solution where the original ferrum 3 the situation the located, and then you have this process of migration, diffusion, where the species move, okay, towards the electrode surface. Yeah. So stirring, of course, is much more is very helpful, so that you have a very what we call homogeneous process. Okay, and then the electron transfer is of course very much easier to happen if we have stirring. Yeah? So let's see, here we have plumbum electrode, okay, and then the other side we have this is working electrode, okay. So this is a very conventional setup. You have, sorry, this is this is working electrode, and we are using platinum, but platinum is an inert, so it's just serve as a solid base, and the analyte that we have is plumbum chloride, and we have supporting electrolyte of potassium chloride. And then we have counter electrode, okay, silver counter electrode, and of course the reference electrode. So this is what happened if we supply, okay, for voltammetry, okay, if you remember the electrolytic cell, not hydrolytic, electrolytic cell, okay, you have to supply potential, okay, for the reaction to happen, okay, and that reaction will produce current. So this is back to the what we have studied in undergraduate, so probably during during school time, okay. Potential voltage has to be supplied, okay, to the system, and the reaction happen, the redox reaction happen. So when the redox reaction happen, there is electron transfer, okay, and current will be current is produced. So this is the whole process actually. Potential being supplied, redox reaction happen, and current will be produced. Okay, so analyte selectivity, okay, I hope that you understand, means that how do we know if we have a mixture of a few metals, right? If we have plumbum, let's say we have copper, we have magnesium, okay, in the same solution. So how do we know which one will undergo redox reaction or which one will not? Okay, so this is the what we call as electrode potential. So this electrode potential is supposed to be, not really, but it's supposed to be very specific towards the metal. So if we supply potential, for example, negative 0.13, then we can make sure that the one being reduced will be plumbum, not potassium. Yeah, will be plumbum, but not potassium. So this is how we control the the process of identifying uh, what the metal inside the sample, okay, by applying specific applied potential. And then when the redox happen, we can observe the current. So the current will relate to the concentration. The current will relate, the resulting current reflects the activity, or in other words, the concentration of the species of interest. Whatever species that you wish to identify and to measure. So this is a very good technique, quantitatively as well as qualitative. But of course, it has to be supported with other technique, for example, spectroscopic technique. Okay, so I think this one. Okay, so you can see this is the movement of ions towards the electrodes. Okay, so this among the process, there are concentration gradients. Okay, let me go back. Okay, so this is what happened when we talk about movement of ions. It does requires time for the plumbum to move, and there are also KCl here as supporting electrolytes, and you can see that you need to stir to make sure that all these layers of sodium plus is not covering the electrodes. Okay, so this one you can see layers of sodium plus, potassium build up around electrode, stop the migration of Pb2 plus, which we do not want. We want Pb because we want plumbum 2 plus to be measured. So this is some issues that you have to take care of. All right, and so back to the Nernst equation just now. Okay, Nernst equation. So this is the voltage that we apply, and this is the standard electrode potential. If it is for plumbum 2 plus, then you can, because it is a standard, just like certain values, molecular weight. So there are standards that you can search. So this is, there are ways to calculate this. N stands for number of electron. And this is usually easiest way to remember is product over reactant, concentration of product over reactant. But this one is no need, it's not for you to memorize because you don't need to do any calculation for this subject, but for you to understand. So the whole process, this is what happened when you start to apply voltage, potential. Okay, you can see that from here, no current observed. Okay, and then from here, you start to have current. So that is when the reduction oxidation start to happen. And this is the maximum current, showing that the amount of the metal, the one that we measure, plumbum 2 plus, that is the maximum concentration that we have inside the sample. So you can identify. All right, let me. This is much easier to look at. Okay, but this one is using cadmium. Okay, we want to identify cadmium 2 plus. Okay, So this is, for example, the potential that will make the cadmium 2 plus undergoes redox reaction. Means that if you use potential 0.8, it will, 0.4, then you can see the reduction of cadmium 2 plus does not happen. Yeah, it's because you can see that the current is very low. This is what we call as residual current. So the actual current starts from here until here. So this is all right. Let me finish. Okay. Okay. So where are the? It's difficult using this. Okay, let me go back just now. Okay, so at the beginning, currents start to be registered here. Okay, this one is residual, means that whatever in the beaker. So this is where we start to have what we call as the redox reaction of this process, the cadmium 2 plus 2 electron, and this is the voltage that's when the cadmium is being started to reduce. So current at the working electrode continue to rise as the electrode become more reducing and more cadmium 2 plus are being reduced. All right, and then we have okay. This is the one that represent the concentration. Yeah, the concentration of the current. So we still have to do calibration plots using different concentration of cadmium 2 plus to identify, okay, this level of current represent what concentration. Yeah, so this is how it happens. Yeah, so this is called limiting current, and this is what we call as half wave potential. Okay, that is supposed to be unique for different analyte of interest. If it is cadmium 2 plus, you have different E half potential, half wave potential. But if it is plumbum 2 plus, you have different half wave potential. But it's not, of course, as specific as, for example, mass spec. Okay, it's just as a guidance. But it is quite robust technique. Yeah. So let's say, for example, if we have a mixture of two different species. Yeah. Okay. You can see, you will see a different half wave potential. Okay. Right. And then this will indicate, okay, you have two different species in the sample, right? And here shows you the concentration effect. You can see that the half wave potential is the same, meaning that you have the same species, but due to concentration, you have a different intensity of current. Yeah? So you can see that this one is the highest and this one is the lowest. Yeah. So it's a very good technique somehow if you know how to use it. Yeah. This one we didn't discuss. I never did any titration yet by using electrochemistry. Okay. And of course, under this voltammetry, we have so many what we call as techniques as well under voltammetry itself. So one, what we call as pulse voltammetry, and to be exact, we have differential pulse voltammetry, and this is the example of differential pulse voltammetry. In short, we call it DPV. D. So this one, okay, is very selective. It's very sensitive. Okay, and you can see that we can quantify the concentration. We can key in the certain voltage that we know for example, for certain analytes, and we can identify we can calculate the concentration after we have done a proper calibration plot. Yeah. So this one is under one technique under voltammetry. The other one is cyclic voltammetry. So usually we use cyclic voltammetry. It's not for quantitative. You can, but it's not, we don't really use it for quantitative, but it's more on the process. If we have like unknown, but we know that it is electrochemically active, we can run cyclic voltammetry and then identify whether it's a reversible process, means that it can be reduced as well as oxidized. Okay, so you can see this is an example of what we call as a reversible reversible redox process. Means that the compound or the species can undergo reduction, and after that it can be oxidized as well. Yeah? Depends on the potential. Okay, if we apply a wrong potential, then it might not happen this way. So first, usually when we want to study certain analytes, we do cyclic voltammogram first. Okay, identify the process. Is it reversible or irreversible? I will show you an example. I think I have irreversible process. And then when we need to detect how much, how low you can detect, then we use differential pulse voltammetry. Okay, I think, okay. Initial current, okay, in this case, the species that we are detecting is ferrocyanide with supporting electrolyte of potassium nitrate. Okay, you can see it just like we have described before. At the beginning, no current. Then you start to have the current where the reduction start to happen. Okay, and then rapid increase in current as the surface concentration decrease, means that lot has been reduced. Okay, and then this is reduction peak. It is called reduction peak. Okay, cathodic means it's a reduction peak. Okay, then we have current decays. Okay, I think you can see. Current decays rapidly as the diffusion layer is ended further from electrode surface. All right, and then scan direction switch. Okay, and then it goes to oxidation as well. All right, so reduction, cathodic peak, and then oxidation is called anodic peak. Yeah, anodic peak. So this one is anodic peak, referring to the oxidation of potassium ferrocyanide just now. Yeah? Okay. And then of course it goes back, it start decreasing as the accumulated ferrocyanide is used up at the anodic reaction. And let's say if we keep running the CV, okay, then you will have multiple different layers. For example, and then you have, okay, so you can run until a certain point just to look at the process, because there are some interpretation that you can do with the process, but this is not what we're going to discuss today. Okay, and then from the cyclic voltammetry, these are important information. You can identify what we call as working area. Electrode area means that it's not the area that we measure on the electrode, but it's the working area, the functional area. So this is through calculation. And then we can also calculate the concentration. Of course, the scan rate is one of the parameters that we can control in the potential set. And we can also calculate diffusion coefficient. I think we have the, So I think this is the last one. So this is the equation, yeah, that you can use, okay, to identify the electrode area, diffusion, and see the concentration. So usually this is what we study first to characterize the ability of the electrode. Okay, so I don't know why it goes back. Should be in. All right. So I think this is what voltammetry is. Okay. So I'm going to show you some examples. So I have to skip this. Okay, just a moment. Okay. That's all right. Okay, my battery is I'm trying to open another hopefully this here. Just a moment, yeah. So I just want to show examples of what researchers, not just researchers, but commercial companies has come out with by using electrochemistry. So there's a lot of actually in the market that we do not know about. Yeah. You can see that this is an example from Siemens. Okay. Before this, we know Siemens is a producer of mobile phones. Yeah? We know they are, but no longer focusing on mobile phones, but they are focusing on medical devices. Okay, and this one, these machines, is to detect what we call as coagulation, because some people have problems of blood clots. Their blood keeps clotting, so they have to check their blood clots from time to time. So this is an example of electrochemistry being used. And this one, at the size of credit cards, debit cards, you can see that obviously there are electrodes. So here they have multiple analytes can be analyzed at the same time. So you have glucose, you have cholesterol, or some other, for example, important that I forgot the important that you have to test, yeah? But you can do multiple analytes at the same time. And the electrical, the electrical circuit is quite simple, and it's actually can just be printed on a very small size, yeah. So it's not that the beautiful thing about using electrochemical, that it can be miniaturized, can be made a very small size. So imagine you can keep this inside your wallet or inside your handbag, so you can do simple testing anywhere. Okay. So this one also is it is I don't know whether it is wearable or they can this is what they call it implantable, but I don't see it is implantable. You can analyze multiple analytes, oxygen, glucose, lactate, urea, at the same time. So you can see that actually underneath the sensor, there are micro needles, micro needles that actually goes through your skin, but it's not painful because it is micro needles. And by using this, they can analyze a lot of biomarkers, okay, to check on your health status. Yeah. So this one I have discussed. Okay. This is I don't know. This is partly electrochemical or this is optical. Okay. This one is Enos. Okay. So this one. Since the electrode also can be printed on your clothes, yeah? So it's possible that we can have the sensors embedded in our clothes, in our shoes, or in our whatever that we wear, or we can have this. Yeah? So this is Professor Joseph Wang, who tried before to come up with what we call he called as field hospital on a chip. Means that it is for soldiers, if they are under certain conditions, they can't call for help, but at least the indicators, where of course underwear is where there are a lot of secreted biochemicals from our body. So imagine that if the soldier is injured, then there are of course some indicators that can be released on the underwear. And of course, if we can have the electrode printed and all the electronic parts there, even the data can be transported remotely to the headquarters. So helps can be sent straight away to the those who are injured. So you can see that electrochemistry is very robust. And of course, I'm using it for biosensor, chemical sensor. But apart from that, there are a lot of other applications in other types of samples. For example, if some of you are working in paints, there are electrochemical also being used to study corrosion. Yeah. So there are of course other applications as well, right? So I think that's it. And I just want to show to you as well that in the value of biosensors. Okay, this is until 2022, but now the value is much higher to 2020. They have actually studied until 2035. The value, the market value is getting higher. So for those who wants to invest, please do invest in biosensors. Okay, and you can see that healthcare, home healthcare diagnostic, and point of care testing. You can see the red and the blue one is covering a lot on the biosensors itself. So point of care testing means that is actually testing on at the bedside. Yeah, because you know patients sometimes you cannot bring the patient here and there, and it's a bit too late to take samples and take to the lab, so they have to do the analysis right there at the bedside. So that is what we call as point of care testing. And home healthcare diagnostic is the one that everybody can buy and do the analysis at home. You don't have to go to hospital, you don't have to go to clinics because you are too lazy or too busy, but at least you want to do a regular checkup, so you can do at home. So this is the business point of view for biosensors. And of course, this is a COVID test kit, I have presented before, right? And there's a lot of startups, okay, on biosensors itself. So as I mentioned, if you're interested in forming or investing in near future or in new technology, so please do look at biosensors. Yeah. And if there's another one that I want to show you, global biosensors market, you can see that electrochemical is the majority because it is in fact a robust technique. Yeah, I think that's it. Thank you so much, everybody. It's not an easy subject, but I hope that everybody gains some knowledge from our discussion. Any questions? Yeah. No question, yeah? So
No, Prof.
if there is no question, at least you can have some ideas how good, not to say how good, but at least in future, it's a good investment. And we, even biosensors or sensors in general now is one of the key points that our country is looking at. Yeah? There's few that they are focusing on, and now they are focusing on more on medical diagnostic. Yeah. So now I think that's all. Okay. So thank you so much to bear with me. All right. So have a good rest. Thank you so much. Okay. Bye bye,
Thank you.
everybody. All right.
Thank you,
Thank
Prof.
you. Bye-bye.